or the rules rather. You're driving down the road, you've picked your spot. If your spot is already taken, you park in the very next spot that is open. If there is not another open spot, that means that the decision has failed. Not everybody will park. Alright? So to demonstrate this, I need 3 volunteers. I got 1. 2. Okay.
Do I have number 3?
Oh, sorry, I thought you were number 3. Come on up.
3.
Okay. So what you're going to do is each take a piece of paper and a marker, write down a number 1 through 3. Don't show anybody else what it is. It doesn't matter what it is. Just pick a number 1 through 3. Okay, and line up right here in any order you please. Doesn't matter what order you're in. Okay, you're first. So what number have you chosen? 2. Okay, so you're going to drive along, and you're going to park in parking spot number 2. So stand right there. That's where you parked. What is your number? 3. Okay, so you drive along. Your spot is not taken, so you park there. What did you pick? 1. Okay. So this is a successful parking sequence. Okay. All right. Stand back here the way that you were originally. Stand back here again. Okay. Hold your numbers up. So the way that we read a parking sequence is just like this. Driver number 1 chose number 2. Driver number 2 chose number 3. Driver number 3 chose number 1. So the way that we're going to write that is like this. We have 2, 3, 1. That's how we label a parking sequence. Okay? So come back over here to the table, scratch out your number, write down another number. It could be the same number, it could be a different number, it doesn't matter.
The key idea is that you don't consult each other.
Yeah, just don't consult each other, it doesn't matter at all. Okay, and line back up any order you want, doesn't have to be the same order. Okay, whatever you have this time. 3. So you drive along. 3 is free, so you'll park. 1, you park in spot number 1. And 3. Now you drive down to spot number 3. Remember, our rule says that if your spot is taken, you take the next spot. But there is no next spot. So this is an unsuccessful sequence. So get back over here the way you were. And we had number 3. This was our sequence. And it failed. Alright? That's bad news. Okay, alright, thank you. You guys can sit down. We'll talk a little more about this. So, now that we know what a parking sequence is, what a successful parking sequence is, can we, why don't we take some scratch paper and try to write down a couple of our own. Say, try to come up with your own successful parking sequence. We already have one. 2, 3, 1. And if somebody thinks they have a successful one, then we'll stand up here and demonstrate how it would work. Or if somebody has an unsuccessful one, we'll come up here and show how it works. Or why it's unsuccessful. So take a minute to do that. Yeah.
1, 1, 1.
1, 1, 1 is what?
Successful.
Successful. Okay. So the suggestion here is 1, 1, 1. And let's see why that works. I'll be all 3 drivers. All right, I'm driver number 1. I come in, I've chosen spot number 1. This is where I stand, or this is where I park. Driver number 2 comes along and says, oh, I chose number 1, but number 1's already taken. So I go to the next available spot, which is number 2. All right, driver number 3 comes along, he says, I've chosen number 1, but that's taken. The next spot, number 2, is already taken as well. Next spot, number 3, is still available. This is where I park. Everybody gets to park. It was a successful sequence. So this one works. Do we have one that doesn't work?
Why are you able to cycle past 1 to 2 and not loop back from 3 to 1?
Well, looping, if we have time, we are actually going to talk about what happens if you're parking on a cul-de-sac. Because that actually will help us to solve this problem. But right now we're saying that our rule is there's a giant cliff at the end and you can't turn around. Impossible.
You just drive off of it.
And also on your way home, your transmission went in your car, you don't have reverse anymore. Any myriad reasons why you can't turn around. But that's our rule right now, that you can't turn around. Okay, do we have somebody who has found an unsuccessful one? 333. Okay, so this one doesn't work because driver number 1 comes down here, chooses spot number 3. Driver number 2 comes along and says, well, spot number 3 is taken, and there are no more. I've driven off the cliff. Does this third spot even matter at all? Because we had already failed with the first 2. So this is our first pattern that we see. That we could have 3, 3, anything, and it fails. So this is a pattern that fails every time. Do we have something similar that will succeed every time? 111, or in particular 11 anything. Because 1, you take that, next spot takes 2, and so it doesn't matter what this person chooses, they're going to get spot 3, that's all they have. Okay, where do we want to go?
I'd say talk about it with your groups and write up some more.
Okay, so what I want you guys to do now is at your tables, and we can wander around and tell you guys some things. Let's try to find certain criteria that will either say this is always successful or this is always unsuccessful. There are a couple of cases where you will absolutely know, hands down at one quick glance, this won't work. And there's another time where you can look at it and say that will work no matter what. So talk amongst yourselves, and we'll be walking around the house for the next 20 minutes. You guys already know, right? Have you found any more unsuccessful ones? All right, take it.
What's that one?
So have we figured out any success killers yet? Something that will say this will never ever work? Or something that says it will always work? What do you have? Sorry, what? Yeah, that's another successful one. 1, 2, 2. 3, 3, 3 is bad. Yep, we got that one right there. Thank you. 2, 2, 2 is bad, yes. That's bad. Now, it's not a universal property, But there is something over here that several of them have in common that is a killer. It will make it not work every time. In particular, what is similar about these three? They're passing one. So what happens if nobody chooses one? Then you've got three people in two spots. Never going to work. If nobody chooses one is never the next spot after anything. So if nobody chooses one, that's automatically bad. Right? So that means we can automatically start writing a whole bunch of things over here. I'm not going to write them all. So that's one of our bad things. And knowing that will help us begin to try to come up with a number of how many successful parking sequences are there. It's a fair question. Another question might be first, how many parking sequences are there altogether? So each one of these is a parking sequence, and we've divided them into successful or not. But how many sequences are there altogether? How do we figure it out? How many? How'd you get that? Yep. So this is the basic counting principle. We have three different places, and in each place we have three decisions to make. Or three options. So 3 for number 1, 3 for number 2, 3 for number 3. 3 times 3 times 3 is 27. Alright? Now what we know is that if 1 does not show up, it already fails. So that already cuts down the number of possible successes that we have. Alright, so we have 27 possible choices. How many of them do not contain a 1? So how many of these can we write that do not contain a 1 in them? 8. By the exact same idea. We have 3 positions, 2 choices for each one. So we automatically know now that from our 27 total, we've come back 8. So that leaves 19 maximum that we could ever possibly have. And we know that there's a possibility of having a 1 and still having it not work. So the bottom line is, there's 27 options. We could list them all and then figure out how many successful ones there are. But I want to talk over here on the successful side. We've come up with one guaranteed unsuccessful criterion. What can we think about something that will guarantee us that it's always successful? Just by looking at it, you can tell that this thing is successful. Has anybody come up with more successful ones yet? How about over here? Have you got a successful one yet?
No, you've listed it, bro.
None that's up here? None that's not up here? Okay, let me give you one. Let me give you one and see if we can figure out something that makes this work. Alright? I claim that the most basic one that you can imagine works. First person chooses first parking spot. Second person chooses second parking spot. Third person chooses the third one. This works. Everybody gets what they want. So that's nice. Everybody's happy. So what's special about this one that we haven't seen a lot of? Well, we saw it up here. What do these two have in common? Feel free to blurt anything out, it's okay. What do these have in common? You guys have this? Say again? It has all the numbers. If every number gets chosen, then no 2 people have chosen the same number. So you never have anybody having to pass over their own spot. So this is good. If you look spot that they want. So there are some other things, but we're going to move on. There are other things where you can look at it and you can say this doesn't work. And there are other things where you look at it and you can say this does work. All right, but I just wanted to really drive home that there are these things that we can look at. But we're going to move on from there. What are we doing next? What's that? Oh, you want to throw that right in there? Yeah, sure. Let's do it. Yeah, we'll throw this in. Okay, so if we're going to attack the main obvious question here, the thing that I've been leaning towards is to say, how many successful parking sequences are there? All right. There are a couple of things that we can do that lead us towards the answer. But what tends to happen, there's two things that you can do to try to solve this problem. If you do it one way, you will find a pattern. And there is a pattern to find. It's hard to find. But there is a pattern. But I won't really tell you why. It'll just give you the answer. Which is satisfactory for some people, but not for others. So the pattern would be that so this would be the number of successful sequences All right, let's do this first. Let's start out with something very, very, very basic. Let's say we have 2 parking spots and 2 people. So even more basic than this. All right, so using our basic counting principle, how many possible parking sequences are there? How many? 2? No, not quite. 2 times 2 is 4. So there's 4 possible parking sequences. Let's just go ahead and write them down. Nope. Okay. We got this here. So we're going to write down the first couple of numbers of the pattern on our giant Post-it note. So I'm going to say for 2 parking spots. What are the parking sequences? Well, we know there's 4, so they could both choose 1. They could both choose 2. They could, first person choose 1, then 2, or 2, then 1. So which one of these work? All right, well, which ones can we say right off the bat that they work using our rule from a second ago? Which 2 work automatically? So this one works. I'm going to check them if they work. Which other one works? 1, 2? What do you think works? 2, 1 works. So why does this one work? Wait, why can we say automatically that this one works? Yeah, it shows both numbers. All right, and does this one work? One reason you can just check it, but another reason there's no 1s. So this doesn't work. So that means that for 2 parking spots, we have 3 successes. So that's cool. I can do 3 underneath. Well, 3 is long. Yeah, I can do 1. So for 1 parking spot, how many parking sequences do we have? We have 1 person choosing from how many parking spots? 1. 1 times 1 is 1. So for 1 parking spot, we have 1 success. Now for 3,
Did anybody list them all out?
has anybody listed them all out?
How many?
Successes are you do you have? How many? 16. That's right. So for 3 sequences, for 3 parking spots, we have 16 successes. And this was done just by brute force, we call that in combinatorics. If you just sit down and figure them out, there are 16 of them. Out of our 27 options that we have 16. Okay? Now, if you wanted to figure this out for 4, you could sit down and figure it out. It would be,
Guesses?
okay.
You guys guess a pattern? We'll let you know.
So our pattern so far, our first number is 1, our second number is 3, our third number is 16. That's not a lot to work with. Okay? Any guesses on what the next number would be? Not easy.
96.
96. I think that is not 96.
But why do you guess 96?
The difference between 3 is 2 divided by, so there's 8 to 16. So the difference between 16 and 3 times 8.
Okay.
That's certainly, yeah, I mean, like, the problem, like, with only 3 numbers, you can always come up with the next number that works, but unfortunately it's not what we need here.
Okay.
What is it? Okay. So who wants to know what the next one is? I can just tell you the number, and then we're going to change the problem a little bit, and we'll see where that number comes from. 175. Too high. Too high. Okay. The next number is 125. Even if I tell you that, it's still hard to figure out where it comes from. All right. Not an easy task to do. So let's move on. And what happens very often in mathematics is that you're trying to solve some sort of problem, and it's hard. So
You agree?
So what you do is you get on Facebook for a little while, then you go to lunch, and then you come back and you say, actually, you know what? This problem that I'm working on is actually a specific example of a bigger problem. All right, sometimes you actually have to beef up your problem, which may seem harder, but the problem actually becomes easier. And that's what happens with this guy. All right? So our harder problem that we're going to do, or rather our bigger problem, not necessarily harder, but our bigger problem is now we've removed our cliff, we've fixed our transmission, and now we can drive around as many times as we want. All right? So here's the 2 big changes. Now, if you miss your parking spot, you can go around until you find another one. So it's possible now that your parking spot was number 3, and that 3 and everything else was taken. So you drive past 3 all the way around and then parking spot 1 again. So this is now an option. All right? What else can happen now is, what else is different now? And this is the real glaring difference. And this is a leap of faith that you just have to trust me to say that we're going to get somewhere. This is what I mean by beefing up the math problem to make it a little easier. We've added an extra parking spot. All right, still the same number of cars, but now an extra parking spot. So when everybody's parked, there will be 1 empty spot. All right, and we do this for a reason. So now we're doing a roundabout sequence. All right, let's say we're going to do 5 cars in 6 parking spots. All right, so we're going to say 5 cars, 6 spots, and let's come up with a parking sequence. So we're going to come up with a 5-car parking sequence just by spitting out numbers. Somebody spit out a number 1 through 5. Doesn't matter. 4. Another one. Another one. 3. We need 3 more numbers. 2. Keep it going. 2. 1. Let's repeat one of the numbers now. 5. Well, that's not a repetition. 3 again. So let's try this. All right, we have 5 drivers. They've chosen 5 spots. This is what's going to happen. Driver 1 is going to come through. Here, let me draw the cul-de-sac. So this is spot 1, spot 2, spot 3, spot 4, spot 5, and spot 6. So driver 1 comes around. And driver 1 parks in spot 1. Driver 2 comes around. Their spot is spot 3. Sorry, that's driver. This is not dry erase. Did anybody ever see me try to do that? Been teaching on a dry erase board for too long. Okay, so driver number 2 comes around and parks in number 3. Driver number 3 comes and parks in number 2. Driver number 4 wants to park in number 1. Driver number 5 wants to park in number 3. They come around, blah, 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 blah. Spot 3 is taken, so they come around and park here. This is a good example. Because have we utilized the fact that we're on a cul-de-sac here? Can anybody go all the way around? No. So what does this tell us about how we beefed up our math problem? Why is this a beefing up of the previous problem? It's kind of an open-ended question. All right. What happens if I were to have tried this parking sequence on a one-way street? Would it have worked? It would have worked. Because I didn't have to loop around. That means I could have just taken my road, stretched it out here to a one-way street, and it would have worked just fine. Alright? And this is what I mean when I say we beefed up the math problem. Because that tells us now that every single successful parking sequence that we had before can be thought of as a successful cul-de-sac parking sequence. Yes?
Should we maybe do some examples?
Absolutely.
List some parking sequences for the cul-de-sac, the roundabout problem. List them as successful or unsuccessful.
Alright, so start doing some ones on your paper. Now I have chosen up here 5 cars and 6 spots. You can choose something smaller if you want. But do it just like this. Just come up with the sequence and then try and see what happens.
The one he wrote for his example was 5 cars with 6 spots. But if you want, you can do less cars. You want the number of spots to be 1 more number of cars. So
Okay, so let's try to find, if somebody finds an unsuccessful one, tell them. Alright? So let's just write down a sequence like I did up there with 4, 3, 2, 1, 3. Just make it up. Yeah, 125. Hey, they just try to really big one. So let's write down a couple of them and let's come up with some. Got one yet?
Wait, will you find unsuccessful?
Well, just try some, and if you get one that's successful or unsuccessful, we'll write it up here.
What is any?
Any is anything you want. I have chosen what we did up there. I chose any was fine.
N is the number of parts as far as you have to go.
Yeah. So when you do an actual example, you can say I want 4 cars, or I want 5 cars and 6 parking spots. Yeah, whatever it is. Everything seems successful so far? All right, well, why don't you spit out a couple of clues and I'll write it up here. 5 ones. 5 ones. Have you got one that requires you to go around a cul-de-sac yet?
5 twos.
5 twos. So we see a pattern here. We can certainly come up with those all day long.
And then you can go 5, 6, 5, 6, 5.
Yep. So we can do 5, 6, 5, 6, 5, something like that. Have you found an unsuccessful one?
All sixes.
Well, that's actually successful.
This table thinks that there are no unsuccessful ones.
You got one? What do you got? 4 twos? And what else? How about 2 ones? 4 ones would work as well. Oh yeah, I got too many numbers here. There we go. Augmented the truthiness of my piece of paper now. Okay, so our list is getting long here. Our list is getting, well, not getting any bigger here. And we have a conjecture from this table that says everything is successful. Well, why is this true? Or why would this be true? Alright? What makes the one-way situation unsuccessful is that you get to the end and you can't turn around. Well, we fixed that problem. It's no longer a problem. So that means that no matter what you do over here, it will always be successful. Not only will it always be successful, but we'll always have an empty parking spot on top of that. And that empty parking spot will be very useful to us in a second. So there are none here. Okay, so now it's very easy to count how many successful parking spots there are, or sorry, successful parking sequences there are, because they're all successful. So using our counting principle, how many successful parking sequences do we have in the case of 5 cars and 6 parking spots? Well, we need to choose how many choices do we have for each spot? 6 times 6 times 6 times 6 times 6. So we have how many? All of them, which is 6 raised to the 5th power. Okay? But in general, so this is just because I chose these numbers, but in general, if I have n plus 1 parking spots, what's my formula going to be? Instead of just choosing a number, I now have n plus 1 to the power of n. And they're all successful. Okay? So now, what we want to do is we want to talk more about this empty parking spot. Alright? So we want to know if we want to solve this initial problem. Alright, we want to solve the problem of how many of these parking sequences are there. You know, not how many of the cul-de-sac parking sequences are successful, Because this was easy. We beefed up our problem to make something easy. So now what we want to do is talk about the relationship between these two. Now, what did we say the relationship was a second ago? On the first example that we did, over on this example here, remember that we sort of accidentally came up with a successful parking sequence in this case. All right? And there was one thing that I said that made us kind of acknowledge that this was successful in this sense, because what parking spot did we not use? The sixth one, the last one. All right? So we said, if the last one is empty, then we have this guy here. So let's write that to make sure that it's sticky. All right? When you use this notation, if the n plus first, or you could say the n plus 1, which I've always found to be comical. So the n plus first, the n plus 1 space in the, I would say roundabout, in roundabout is empty, then we have a successful one-way parking sequence. All right. So this is our big connection. This is our beefed up math problem taken back down to size. All right. If you generalize a math problem, you better make sure that your old problem is a subset of your new problem, which is what we have here. All right? So that's cool. All right? But now, and we're going to think about this for a few minutes, now we want to say, here we have the total number of roundabout parking sequences, n plus 1 to the n. We want to take this number, do something clever to it, and somehow get the answer to this question. So we're going to take all of these sequences that are successful. We're going to use this fact and try to come up with some way of getting these numbers that we had before. So we'll spread out, we'll talk about that for a few minutes and see what we can come up with.
extra, the one you're going to fill up until you get to the one before it.
Okay, so is this true when they're not all the same number? Like, let's take, I wanted something a little different. Where's this one? 4, 3, 2, 1, 3. Which did this leave open? Spot 6? What if I increased them all by 1? What does 5, 4, 3, 2, 4 leave open?
Spot 1.
Spot 1. The next guy around. So how can we use this idea to count the ones where spot 6 are left open? We use this idea that when we increase your preferences by 1, the next spot is left open.
What spot would that be open? Right now, this one, this leaves spot number 1 open. Increase everything, it leaves spot number 2 open.
Great.
So on and so forth. So we want to try to use this. This is not an easy problem, so don't get frustrated or anything. But it's something to think about. We're trying to figure out some way that we can take this number and decrease it in some way, because what we want to do is from this number, we want to figure out all the spots that leave, all the parking sequences that leave number 6 open, or leave the last one open. That's what we're looking for. So think about it for a minute. Whatever we come up with is going to involve this, and it's going to give us these numbers. That's what we're going to be looking for. Okay, it's hard. All right. It's hard. When I saw this, I've been doing math for a long time, and when I saw this, I said, wow, that's clever. I really enjoy this. Now, I could just give you the answer, but it's not as fun as forcing your way through it. All right? So what happens is, like Perry was saying, when you add 1 to all of these things, you shift the parking spot that's empty. And we don't care about this road here, it just shifts it around like hours on a clock. Like that empty parking spot, which is moving counterclockwise around the cul-de-sac. Now what the connection is that you have to make, the connection is that there is nothing special about spot number 1, or spot number 2, or spot number 3, or the last spot. They're all exactly the same. They all show up the same number of times. Alright? And since they show up the same number of times, that means we can take all of our parking sequences, all of these guys, and we can say that each parking spot is empty the same number of times.
So would you divide that number by n?
By close. By how many parking spots are there? They're not
N plus 1.
N plus 1. Very good job. So that's what's happening. Each parking spot is empty the exact same number of times. So that means that each parking spot is empty this number divided by n plus 1 times. One more. So this is the the punchline. Each spot is empty the same number of times. There are n plus 1 parking spots, n plus 1 spots. So each spot is empty n plus 1 to the n divided by n plus 1 times. Yes? Exactly. Correct. Yeah, they would be the exact same thing. That's a good observation. But
in the dead end, that would have been somebody parking in 2, 3, 4, 5, and that last car couldn't have gone in because there was no 6 spot.
But the good observation is that it is in fact the same count. Alright? So if spot 1 is not used, then spot 2, 3, 4, 5, 6, they were used. So if in your parking sequence you just subtracted 1 from each number, then you would have a successful dead-end parking sequence. That would be just fine. But the fact of the matter is, say again? This times 2? No. Because what's happening is, what you're saying is that each parking spot is empty this number of times. That means spot number 6 is empty this number of times. Spot number 1 is also empty this number of times. So certainly spot 1 and 6 together, each one is empty this number of times. So if the question were, how many parking sequences are there where either 1 or 6 are empty, then it would be this times 2. But this is just for each individual spot, which includes 1, it includes 6, it includes 5, it includes spot 796 in a big cul-de-sac, a giant cul-de-sac. Alright? So this is our answer. This is what we're looking for. Now, this is not what you'll see in the handout, because we can simplify this just a little bit using a little rule of exponents, which you don't have to know. But this is the exact same thing. This equals n plus 1 raised to the n minus 1 power. This is the number. Alright, so this is the number of successful dead-end or one-way parking sequences. How did you make that from
the empty spot
to this? Oh, you mean from here to here?
Yeah.
Because this, a dead-end successful parking sequence, is the exact same thing as a roundabout sequence where spot 6 was empty, where the last spot was empty. Yes.
Well, you said that's the number where 6 is empty.
Yeah.
But at the thing before, everything lining.
Yeah.
We have a take away.
But this is taking away by division. We're making the number smaller. It's not actually, we're not subtracting. Yeah, we've taken away a lot by dividing. It's not a subtraction. All right. So this formula is a bigger formula than what we need. It solves more problems than what we ask, which is what you expect. This was a bigger math problem. We solved it, and as a special case of the solution, when the last spot is empty, that's what we were looking for. We just happened to solve the problem of, well, Well, when is spot 3 empty? How many times is spot 5 empty? We solved all of them, but we only needed one. But just to show you that I am in fact telling the truth, let's plug in some values for n and see if we get the answers that we already found. Alright, if we plug in n equals 1, that's kind of hokey, but let's make sure that it works. 1 plus 1 is 2. And 1 minus 1, 0. 2 raised to the 0 power, 1. 1. So this works. That checks out. For n equals 2. Remember, for 2, we straight up figured it out. We just wrote down what they were. So 2 plus 1 is 3. 3 raised to the 1 power, better be 3. So that checks out. And then in the case of n equals 3, we're going to get 16. For n equals 4, which we didn't actually figure out, somebody figured out the 16 for us by brute force, like I said earlier. But if you do n equals 3, well, that's 4 raised to the 2nd power is 16, it checks out. And so then we can do this one, which is 5 to the 3rd power, and so on and so forth. So this is the number of ways that people can choose things, that people can choose their parking sequences so that everybody parks. And not necessarily where everybody wanted, which is a different story altogether. Maybe come to the next circle on the road and we'll figure that problem out. But the nice thing about this problem, so Perry's handing out a handout that covers everything that we talked about and then some. We went a little out of order due to the time constraints. This would have taken a lot longer if we'd gone through in linear fashion. But other things that you can think about. And here's something we didn't go over, but it's very interesting. So earlier, when our intrepid volunteers were choosing their numbers, what would have happened if they chose their numbers, and then they parked their cars, and then I had them do it again when I had them mix themselves up? Does that change anything? The answer is, it changes some things, but it does not change the successfulness or the unsuccessfulness, which is interesting. There are other things like, mixing numbers up, adding 1 to all the numbers. Lots of things that you can do. So, read through this while it's fresh, and you can definitely, you can let your mind wander, you can answer these questions, but the final answer, this stuff is all written in the back, or written on the last page or so. And thank you for coming out, learning about parking cars.